Hello, welcome to video 7.3.1 on electrolysis. So electrolysis is a process in which a non-spontaneous redox reaction is forced to take place when an external source, like a battery for example, is applied. And usually you do this to decompose a compound. So here's some more ideas. A Faraday, as we know, is the total charge when 1 mole of electrons is transferred. And so we've used the Faraday before, but here it is again. Now current has to do with the movement of electrons, and that is the rate at which electrons are moving through a wire. Of course, you can have electrons moving through anything, but here's our rate. We're going to concern ourselves with our wire. Current has a unit of amperes, so 1 amp or ampere equals 1 coulomb per second. Now, this is a conversion factor we're going to use, so maybe highlight that so you can find that easily later. So let's look at the Hofmann apparatus. The Hofmann apparatus is shown below. And that's used to decompose water into its constituent parts, so hydrogen gas and oxygen gas. Now right now, I'd like you to try parts A and B on your own. Write the equation for the overall reaction of the decomposition of water. So that has all of the O2, H2, H2O on it. So we're going from H2O to O2 and H2, make sure it's balanced. And then for part B, the two tubes are labeled H2 and O2. Based on your experimental setup, how can you tell the gases apart? If there were no labels here, essentially, how could you come up with those labels? How could you tell which gas was which? Okay, go ahead and take a second to figure out A and B, and then come back to check your work. Okay, welcome back. So for our overall reaction here, we have H2O as a liquid, and when that decomposes, it yields H2 gas plus O2 gas. Now, of course, this isn't balanced, so to balance this out, I need to put a 2 here and a 2 here. Then we're balanced. So that's part A. For part B, like I said, our tubes are labeled before, but how can we tell? Well, look at the volumes. O2 is half the volume of H2, and that's true also in the stoichiometry here. So we know that our H2 is going to be double the amount of O2, and so since this is gas, it's not liquid anymore. We can tell this is hydrogen gas and it's oxygen gas. And we can tell because we can compare that to the stoichiometry of the reaction. So the volume of H2 will be greater than that of O2. You can also do something else. You can also ignite these gases if you wanted to test that and see which one explodes more spontaneously. They're going to react a lot differently. Hydrogen gas is going to explode quite violently, where oxygen is only a fuel for combustion. So also, the gases will react differently when ignited. Okay, part C. Write the equations for the oxidation and reduction half reactions. For this one, make sure you balance it. Make sure you have the electrons the same on both sides. Take a second and try to write the reactions for oxidation and reduction, and then let me know how many electrons are transferred. Then come back and check your work. All right, welcome back. So the oxidation half reaction, we'll start with that. We're going to take 2 H2O, and again, make sure you're balanced. And that's going to yield oxygen plus 4H plus 4 E negatives. So my H plus and E negative, that balances out my charge there in O2 and H from H2O. So that's my oxidation half reaction. My reduction half reaction, we're going to have 4 H2O plus 4 electrons, and that's going to yield 2 hydrogen ions. Erase that for us. 2 hydrogen gas plus 4 hydroxides, right? We need those hydroxides, those 4 of them, to balance that 4 charge over on the reactant side. Remember, we add hydroxides and we add hydrogens to balance. Also, we have H and OH for H2O. Okay, so overall, we have 4 electrons being transferred, right? So 4 being produced, 4 being absorbed. So 4 electrons are transferred. Okay, part D. Determine the direction the electrons are moving through the apparatus. Label the anode and the cathode. Take a second and see if you can label that down here for yourself. Okay, so we know that we are going to be producing oxygen in the oxidation reaction. So if I'm producing oxygen here, this must be the oxidation half reaction. This oxidation must be happening over here, and reduction must be producing hydrogen gas right here. So we're going to label that hydrogen. Okay, and so we know that oxidation happens at the anode and reduction happens at the cathode. And we also know that electrons flow from anode to cathode, so they must be going this way. Okay, so that's part D. Part E, find the potential for this reaction. What is needed for this reaction to take place? So here you're going to find the overall voltage. So take a second, and I'd like you to write the oxidation and the reduction half reactions, their associated voltages, and then write the overall reaction with its overall voltage. All right, welcome back. So my oxidation half reaction was 2H2O yielding O2 plus 4H plus 4 electrons. And my voltage for that was negative 1.23 volts. And I got that from my table of standard reduction potentials, just like we've been using. So our table of standard reduction potentials, if you want to, if you flip the reaction, as we did here, make sure you flip the sign, because we had oxygen plus hydrogen plus electrons going to H2O. That was positive 1.23. We flipped this. We started with H2O as a reactant, so we have a negative 1.23. Okay, so that's where I got this value from. Now my reduction half reaction, was 4H2O plus 4 electrons goes to 2 hydrogen gas plus 4 hydroxides. And I just looked this value up on my table. I didn't have to do any flipping because it was already the reduction, because it's a table of reduction values after all. So I got negative 0.83 volts. Okay, so my overall reaction here, canceling anything that, well, cancels out, we're going to be losing our electrons there. They are the same on both sides. And we'll just go ahead and write our overall reaction. 2H2O. And that's our liquid. Yields to H2 gas plus O2 gas. And overall negative plus another negative is negative 2.06 volts. Remember, this is only going to be spontaneous if this is positive, which is why we need a battery in this case, right? And so we have negative 2.06 volts. So because the standard the standard potential of the cell is negative, it's non-spontaneous in the forward direction. And it's going to require an energy source to drive it. Now the energy source needs to be greater than 2.06 volts. So any battery that's at least 2.06 volts will do the job. So because, like we said, the energy, right, the voltage is less than 0, it's not going to be spontaneous, and that requires an energy source of greater than 2.06 volts to drive it forward. Okay, so let's take a look at part F. So since water is an electrical insulator, sodium sulfate, Na2SO4, is often added to facilitate the movement of electrons. Why isn't the reduction of sodium ions observed? So why don't sodium ions become reduced? So let's take a look at this equation. Let's go ahead and find this on our table of standard reduction potentials. That's right here. So the sodium reduction, we have a standard reduction potential of negative 2.71. Okay, so let's take a look at the reduction of H2O. So if we reduce H2O, I believe we already wrote that up here, the reduction right here is negative 0.83 volts. That's a more positive number. And so that means that this is going to be more preferentially reduced. Water is going to be reduced over sodium because sodium standard reduction potential is much more negative. So it's not going to be chosen, so to speak, to be reduced first. So the reduction of H2O has a more positive, it's not positive per se, but it's more positive, it's greater standard reduction potential. So water is preferentially reduced over sodium ions. Okay, so right here, our sodium, of course, we found out, we looked that up, that was negative 2.71 volts, and we're comparing that to 0.83. 0.83 is just bigger, so that's the one that's going to be reduced, and the sodium won't be touched. Okay, lastly, part G. If a current of 10 amps is used to run the apparatus, how long does it take to generate 1 liter of H2O gas? All right, so this is the stoichiometry problem. Let's go ahead and give you a second to get started on this, and then see if you can come up with the answer in seconds, and then come back and check your work. All right, I'm going to go ahead and start with what I want to find here in the end. So I'll start with 1.0 liters of H2 gas. And I'm going to assume this is at STP because it doesn't tell me otherwise. So that means I can use my 22.4 liters per mole. So there are 22.4 liters of H2 per 1 mole of hydrogen gas. Then I need to get rid of my moles of hydrogen. I need to go ahead and get into moles of electrons. So I can look at my balanced half reaction and I can find the ratio. So right here, it's going to tell me that for every 1 mole of electrons, for every 2 moles of electrons, I have 1 mole of H2 gas. So we have 4 electrons, 2 H2 gas. That reduces down to 2 to 1 ratio. You could certainly write 4 over 2 here, but it doesn't really matter. I'm just going to reduce it down to the lowest ratio. So for every 2 moles of electrons, there's 1 mole of H2. And so this part right here, this is from the balanced half reaction. Okay, so next thing, I need to get rid of these electrons and get myself into charge in coulombs. So for this one, I'm going to use Faraday. And so Faraday's up here are 96,485 coulombs per mole of electrons. So I'm not going to flip that around. That's just going to stay there in the same orientation. So 96,485 coulombs per 1 mole of electrons. And that is a Faraday. Okay, so now how do I get from coulombs to time? Well, now I use my definition of an amp. So coulombs per second is a definition of an amp. So I can go ahead and plug that in. So for every 1 second, I have 10.0 coulombs. Because look, it's given to us. A current of 10 amps is used to run the apparatus. Well, what is an amp? It's coulombs per second. So you can go ahead and flip that around and use it as a conversion factor, no problem. Make sure your current goes next to the coulombs there and not seconds, because it's coulombs per second. So now we're out of coulombs into seconds, and now all you need to do is plug this in. So we'll write ourselves a note here. Second over coulomb from amps. And when you plug all this in, you should get, let's see, we have 2 sig figs there, 3 sig figs there, so 860 seconds. If you had 861, that would be one extra sig fig, so 860. And that is how we find out how many seconds it would take to generate a liter of hydrogen gas. Now let's try another example. Let's look at something else. So looking at example 2, electrolysis can be used to isolate sodium metal from rock salt, NaCl. So you can take that sodium metal out of NaCl. But in the setup, you need molten sodium chloride. That is 801 degrees Celsius. That is an unimaginably high temperature. It's crazy to get molten sodium metal. Okay, anyway, and that's placed in a cell with inert electrodes. So those electrodes aren't going to be active at all. So usually they use platinum or graphite. And it's connected to some massive battery source, something with power. So for the first part, write the reaction, the half reaction that takes place at the anode and the cathode. So it's already giving us our anode and our cathode here, so we don't need to look anything up. So in our anode, that's going to be our chloride reaction there. So at the anode, we know that the anode is always oxidation. So we are going to be losing electrons, so our electrons are going to need to be on the product side. So 2 chloride goes to chlorine gas plus 2 electrons. So the electrons are given off, we know that's oxidation happening. And the cathode, we know is going to be reduction. And that's our sodium example right here. So we know that electrons are going to need to be absorbed. And so for sodium, we have Na plus electrons, and that's going to yield sodium metal. So looking these values up on our standard reduction potential tables, so we get negative 1.36 volts and negative 2.71 volts. All right, so notice we're not balancing these right now. We don't need to because we're not figuring out the overall amount. So for right now, we're not worrying about that, and we're finding our standard reduction potentials and oxidation potential. Okay, part B, write the equation for the overall reaction and find the minimum battery voltage to run the cell. So overall, what you are doing here is you're taking sodium chloride, that's liquid, because it's at that super high temperature, and you're turning that into sodium metal plus chlorine gas. And in doing so, you need 4.07 volts. So that means that you will need a power source of greater than 4.07 volts to run this. So you need a power source of greater than 4.07 volts to run it. Greater than, not equal to. What is the mass of sodium produced in 1 hour with a 4.5 amp current? I'd like you to take a second, or a few seconds, and I want you to find the answer to this. And we're looking for the amount of sodium in grams. So take a second and see if you can figure out this stoichiometric problem. All right, first thing I'm going to do is figure out how many seconds in an hour. And so that's 3,600 seconds, and in 1 hour. I could have just written hours and converted to seconds, but I'm going to start in seconds. So if I have 3,600 seconds, and I know I have a 4.5 amp current, that means I have coulombs per second already. 4.5 coulombs per second. I can figure out, I can get rid of coulombs by using a Faraday. So I know that 1 mole of electrons carries 96,485 coulombs. And for every 1 mole of sodium, there's 1 mole of electrons being transferred. And now I'm in moles of sodium. I need to get to grams of sodium. So I looked that up on the periodic table. Its molar mass is 22.99 grams of sodium for every 1 mole of sodium. Plugging this into my calculator and keeping our 2 sig figs here, I end up getting, let's see, 3.86, but with 2 sig figs, 3.9 grams of sodium produced over 1 hour with a 4.5 amp current. Okay, so that is it for video 7.3.1, and that is the only video for electrochemistry, lesson 7.3. Thanks for your attention. Bye.